Alright, so we'll look at the basics of organic chemistry using these few questions I have with me. Okay, we'll just go straight into it. We're just like 7 questions. The organic structure below represents a molecule that is involved in modifying protein function by actually reacting with protein molecules. Now the question says, what is the molecular formula? So I don't have to answer this question. I just have to explain to you what to do. So a molecular formula indicates all the number of atoms that are present in a given molecule. Okay. So in this case, if I can give an example, I'm seeing that carbon is present, hydrogen is present, nitrogen is present, phosphorus is present, oxygen is also present. I don't know what else you can see, but that's what I can see. So indicating clearly the number of these atoms existing in the whole compound is what will give us the molecular formula. Now the second part of the question says write its corresponding expanded structure. So these two questions, for you to answer them, you should understand both angles. That means you need to understand the interpretation of skeletal structures. What do they mean when they draw something like that? How do you count the number of hydrogens present? How do you count the number of carbons present? So at every point where there is no other atom, okay? So if I was to draw something like this, at any turning point and at any end point where there is no other atom, carbon is present. You should know that by default. Okay, and then each carbon forms a maximum of 4 bonds. I like calling them connections. So if you look at this carbon there, it's already connected to 2 other carbons, or it's already having 2 connections, so it needs 2 more hydrogens for it to be balanced. And so that's what you do when you look at the entire structure. So I can give an example. When you look at that point, bear in mind carbon is existent. Now it's having 3 connections, so it will need 1 more hydrogen there. So that's how the expanded structure can begin to come out. And so let me just give an example of that part. I'm inside 1, 2, 3, 4, 5, 6. So let's draw the 6 sides that we have. So 1, 2, 3, 4, 5, and 6. So for expanded structure, at every point there where there's none, you put carbon. But let me first of all put what's already in existence. So I can see there is a presence of a nitrogen at that point there. So nitrogen is present. So all the other points would have to put carbon for the expanded structure. Okay. So carbon, 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 carbon. So at every point, turning point, there is a carbon present. So when you're drawing the skeletal structure, the instructions are don't show the carbons and hydrogens except there is another atom other than carbon and hydrogen attached to that point. Okay, so let me not forget that there is the presence of a double bond somewhere there, equally there, and somewhere here. And let me not forget that there was actually nitrogen present down there, so I have to put it. Okay, now if you look at this carbon there's a connection to NH2, so I'd have to put it. So the question you ask yourself, is this carbon balanced? Is it already having all the 4 connections? Yes, it is. We can move to the next one. The immediate one at this point is equally connected to another nitrogen somewhere there. Okay. Then this one at this other point is equally connected to another nitrogen somewhere there. And then there is single bond and a double bond too. So at this point is a presence of a carbon expected. So this carbon is having 4 bonds, that one is having 4 connections as well, so they are already satisfied. This nitrogen is already having the 3 connections it needs. Now this carbon at that point is only adding 3 connections, so that one in terms of expansion will have a hydrogen indicated. Okay, that nitrogen is already having 3 bonds, so we can proceed. This one is having only 3 bonds as a carbon, so we need an extra hydrogen at that point. So this is what you do when you are expanding the structure. You're trying to show the hydrogens and the carbons that were not visible in the skeletal structure. So it just requires you to understand what every 10 represents. So for example, that carbon, it implies it's connected to other carbons at the end. So there is a carbon, there's a carbon there, there's a carbon there, and there's a carbon there. And the carbons at the end are primary carbons, meaning that they've got 3 hydrogens connected to them. So at that point there's a carbon present, okay, which is connected to oxygen, connected to another carbon, connected to another carbon, another carbon. So I've given an idea on how you can go about that, and that's where I will just end for demonstrating the first part of the question. Okay, so feel free to pause the video. Actually, there's no need to pause it before you proceed to the other questions. Expand the full structure, count the number of atoms there are. You'll be able to come up with a molecular formula for question 1. Let's look at 2. So we can actually the organic structure shown below is an important intermediate in the biochemical pathway which ultimately produces purines and deoxythymidine monophosphate, which are needed in the synthesis of DNA and RNA. Calculate the formal charges on all the heteroatoms of this structure. So heteroatoms, atoms other than carbon and oxygen, since we know organic chemistry focuses on the 2. So now formal charge is given to be valence electrons in the outermost shell, subtract the lone pair electrons and the number of bonds. So bonds and lone pair electrons, or non-bonding electrons if you want. Non-bonding electrons are also called lone pair electrons. So I can give an example of this nitrogen there. Nitrogen has got a valence of 5. In this case it has got 4 bonds. There are no lone pair electrons, so it's just 5 minus 4 minus 0, so that's just a 1. So that's a positive 1 as a charge. I can give an example of another nitrogen. Which other nitrogen do we have? This one there. So there are 5 minus number of bonds there are 4 equally, so no difference. Let's look at oxygen now. Oxygen, the one on top, it has got 2 bonds, so 6 minus 6 is the valence, have the valence electrons, and then the bonds are 2 non-bonding electrons, or the lone pair electrons are 4, so that's a 0 charge, no charge. And then if we look at this one, there it changes, right? 6 minus the number of bonds there is 1, number of non-bonding electrons are 6, so the charge is negative 1. So that's just the way it is. You just have to know the group in which the element is, so that group number minus the bonds and the non-bonding electrons. So now some of you have seen this formula before where they say half bonded electrons, so this is fine as well. If you say bonded electrons, it means each bond is going to be taken as 2. So if I look at nitrogen, the number of bonding electrons there should be 8, because in each bond there are 2. So that will still give you 4. So I believe the faster way and better way is just to count the number of bonds. So go on and determine the valence, the formal charge of phosphorus there, and this oxygen, and all these oxygens around that, and that one there. Okay, so that's how you calculate the formal charge. Now look at the third question. Give a molecular formula for a 5-carbon hydrocarbon with 1 pi bond and 1 ring. So a hydrocarbon only contains hydrogen and carbon atoms. So 5-carbon hydrocarbon with 1 pi bond and 1 ring. So feel free to pause the video and try out this question. Alright, so answering this one, we'll start first of all with 5 carbons, right? So 5 carbons in a ring, and then there's a single pi bond there. So 1, 2, 3, 4, and then 5. So that's in terms of the skeletal structure. And so then we know there is a single double bond somewhere. Let's just put it there. Okay. So we've, I think, met all the requirements. 5 carbons, and then 1 pi bond and 1 ring. So we can expand that one for us to easily come up with a molecular formula. So remember, at every point there should be a carbon. So let's put the carbons. So carbon, 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 carbon. So each carbon is supposed to form up to 4 bonds. So the one on top is having 3. So we'll just add 1 to make it 4. This one is having 2. So add 2 hydrogens. This one is having 2 as well, 2 as well, 1. So they're already having 4 bonds now. So these are going to be hydrogens. So we've got CH. How many carbons are they? 5 carbons. How many hydrogens are they? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's how you come up with a molecular formula. Now here they want us to draw the skeletal structure or the bond line structure. So I would recommend you watch a video where I introduce naming, giving the IUPAC names of these structures and also drawing the skeletal structures for you to easily do these questions. But either ways, I'll still explain on how to go about them. But if you want more practice and more understanding, the link is given below. So 2,5 dimethylhexane. So the last part of the name is the parent name. And just to give you a reminder, from the first carbon, it's meth. And then we've got eth. So let me just give you examples of alkanes. So methane for the first one, ethane for 2, and then propane, butane for 4, pentane for 5, and then hexane for 6, heptane for 7, octane for 8, nonane for 9, decane for 10, and so on and so forth. You just end there. So when you see hexane, what I'm seeing there, I'm seeing 6 chain. Okay, it's 6. So 1, 2, 3, 4, 5, 6. Okay, now we can just draw that in a simple way. At every starting point there is a carbon. So 1, 2, 3, 4, 5, 6. That's in terms of a bond line structure. Now we are told 2,5 dimethyl. So there is a methyl at position 2 and 5. So if we are, let's assume we start counting from this side. So position 2, there is a methyl. So that is a CH3. Not CH3 actually. Yes, CH3. And then on position 5 as well. So at that point as well, there is a methyl. Okay. So we can actually remove now the carbon and the hydrogen. Just wanted to show you. So this is the skeleton of the bond line structure of the first one. Okay. Now for the next one, it's heptane, so 7. So 1, 2, 3, 4, 5, 6, 7. Now what are we told? We are told on position 4. So let's assume we started from this side. So 1, 2, 3, 4. On position 4 we have isopropyl. Now isopropyl, propyl first of all is a 3 alkyl, 3 carbon alkyl. So now it's called isopropyl when it joins using the middle carbon. Okay, like that. Now that can be presented as 3 carbons like this, and then joins from that point. So if I flip it and join it on carbon 4, it will be like this, showing that there's a carbon here, and carbon there. So joining through the middle carbon makes it to be isopropyl. Okay, and then on position 2 we have methyl, that's position 2, and then on position 5 we have again methyl. So di means 2. So that's a skeletal structure we are talking about, describing. Then for the next one, I'll just extend this very one. Now there we are told it's octane, meaning 8. So the previous one ended at 7. So just would add an extra carbon like that. So that should be able to be, that's 8. Now there we are told on position 2 we've got 2 methyl groups on position 2. So at that point there, it's like this. So at this point you can actually even change the way it's bending there. You can make it a bit upwards like this, so that this can be like this, then like this. Others would draw it almost in a similar manner where it's like this, so that it can show that if you start taking this to be your first carbon, that will be a second one, and then the second one is connected to 2 methyl groups, so that's why it's dimethyl. And then on the position number 4, that part, there's propyl. So in this case it's not iso, but just propyl. So 3 carbons will be joined. So that's 1, 2, 3. We're done. Now the next one is hexane. Pause the video and try that one out. Cyclohexane, meaning that is cyclic, but with 7 carbons. So 1, 2, 3, 4, 5, 6. How many carbons are we counting? Let me count properly. So it should be a 7-sided. So okay, so that makes it 3, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So that's cyclohexane in itself without adding anything. Now we are told on position 2 there is ethyl. So if you start counting from there, you take that one to be your first part. Ethyl is going to be on the other side. So just a line indicates that there's a carbon and 3 hydrogens there at the end. That's ethyl. No, that's methyl. Now ethyl is something that is like this. There's an extra indicating that there are 2 carbons attached, CH2, CH3. Okay, so that's ethyl. And then on position 1 and 4 we've got dimethyl. So methyl on position number 1, let me use a different color there. So on position 1 and position 4, so 1, 2, 3, 4. So somewhere there we have another methyl. So we've got 2, calling them dimethyl, on position 1 and 4, and then on position 2 we have got ethyl, and then this is a cyclohexane. Now, previously we were trying to draw the line structures. So if you've understood whatever we're from doing from previous question, this shouldn't be a struggle. Question 5 would be easier. So it's actually easier to name if you expand the structure. Okay, so let me just try to expand it for you. So we have CH3 to start with, we have CH2, and then I've got a carbon. So when you see brackets, it implies that's a branding or a branching structure. It's a substituent. It's not in the main chain, but it's connected to the main chain. So we can see there are two. So CH2, CH3. So CH2, CH3. So that's actually, when you see two carbons, just know that that's ethyl as a substituent. If it was just one carbon with 3 hydrogens, that would be methyl. So we have now CH2, CH2, CH3. So the parent structure is probably the middle one, right? No wasting time. So we have 1, 2, 3, 4, 5, 6. So the parent name of this structure is hexane because it's 6 carbon chain. And then the substituents are 2, but they are closest to this side, right? So they are on the, we can count it to, can take it to be on the 3rd carbon. Because if you start from the other side, it will be on the 4th carbon. I want the lowest positioning as possible. So that will be a 4. How many are they? There are 2. So let me call it not position 4, actually position 3. So position 3, there are 2 of them. I'll say 3, 3, and then I'll call it diethyl actually. Hexane. Okay. Just as we saw previously, when they're connected in the same position there, you put the number twice and then put the prefix to demonstrate or to illustrate how many they were. Okay. I'm sure the next one shouldn't be a struggle, so feel free to pause the video and just try it out. Now for the next one, so it is drawn for us. The longest chain is 1, 2, 3, 4, 5, 6. So again, that's hexane as a parent name structure. Now why are we calling it hexane? Why are we not calling it hexane? So it's because there is no double bond there. This is purely an alkane. And then positioning, which side do you think is the better to start from? I believe starting from this side will give us lower positioning. So that carbon 1, this is carbon 2, carbon 3, and carbon 4. So on carbon 2, 2, 2, we've got dimethyl. There are 2 methyls connected on position 2. And then on position number 4, again we have a methyl. So instead of calling dimethyl, it would become trimethyl. So say 2, 2, 4, trimethyl hexane. So that's the full name for that structure. I hope you got that right. You're still at liberty of pausing the video and trying out the next ones. So here what we're trying to do is just first of all determine the longest structure, the longest chain. So 1, 2, 3, 4, 5, 6, 7, 8. That's 8. We start from the top. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I believe that should be the longest. So it's longer when you start from the top. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So let's call that 9. Then this, how many carbons are there? I can see 1, 2, and 3. So it becomes butyl because of 3. No, propyl actually. Then this one is methyl. That also methyl. So since it's what? I'll count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's non-N. Now the shortest possible positioning is would be from this side. 1, 2. So that would be 3, 4, and 5. So on position 3 we have methyl. So on position 4 as well. So that's dimethyl. And then on position number 5 we have propyl, non-N. Okay. Then the last one on this page, pause the video and try it out. What do you think is the longest structure or the longest one? 1, 2, 3, 4, 5, 6, 7. I don't think there's any longer than that. So that's 3, 4, 5, 6, 7. What if we started from the top? 1, 2, 3, 4, 5, 6, 7. Now this is a case where now you have to debate which side has got more substituents. You go for the one which has got more substituents. If we take this one, we're going to have this and that as a substituent, only 2. If we start from the top, we're going to have 1, 2, 3, and that's what's advisable according to the rules. So go for if you've got 2 equal length chains, go for the one which is giving you more substituents. So we'll go for this one. Instead of having isopropyl, we're going to have 2 methyls and 1 ethyl. So this is ethyl, that's a methyl, so Me, then equal this is M. How many carbons are there again? 1, 2, 3, 4, 5, 6, 7. So hexane. Which side will give us slower positioning? Obviously, if we having any side, if we start from the top, that's going to be position 2, 3, 4, 5, and 6. So from the top, it's 2, 3, and 6. From the bottom, it's 2, 5, and 6. So from the top, it's better. So we'll say 2, 6. It's at 2 and 6 where we have dimethyl, and then on position 3, that's where we have our ethyl, so hexane. Okay, so that's how simple it is to actually name these structures. Okay, so now look at all these questions that are ahead of you. So just register on our site, you'll be able to access all these, okay, in solution form, in video form, and PDF. So all these are named for you and are readily available for you on the site. Okay, so primary, secondary, classifying them, and actually you have access to the entire full topic organic chemistry on our site. So that's better, and you understand the topic in full. So are you wondering how to name all these and actually practice more structures? Just register on our site. The link is given in the description below this video.